Welcome to our Back to Through Inquisitive Kids. In this video, we will be looking at determining linear functions using systems of equations, expressing the linear function using corresponding systems of equations. This is part 2 of binary linear equations and linear functions. As you may recall from the last lesson, we learned about the relationship between binary linear equations and linear functions, and how they relate to each other algebraically and geometrically. If you haven't watched that video yet, be sure to go into the description box down below, and I'll be putting the link to that lesson there. Learning goals. The expression of the linear function can be determined by using a system of linear equations in two variables. So let's do some review from the last lesson. What is the relationship between a system of linear equations in two variables and a linear function? Well, the relationship is that the solution of a system of equations is equivalent to the coordinates of the intersection point of the corresponding two linear function graphs. And conversely, it's the same, right? So the coordinates of the intersection points of the two linear functions graphs are also the solutions to their corresponding systems of equations. And we talked about how this is true, because according to definition, one of those functions is just a whole series of possibilities of coordinate pairs that satisfy that one function. Another line is a set of coordinate pairs that satisfy that function. The point where they intersect is the one point in the entire Cartesian coordinate system that satisfies both of these equations. 2. What are the different ways to solve for solutions to systems of linear equations in two variables? Well, previously we learned how to eliminate variables, right? The substitution method and adding and subtracting the two equations. Those are all algebraic methods. Graphing is also another way. We could graph each of the equations in the system as their linear function on a graph and find their intersection point. But that usually is less accurate. Determining the expression of a linear function using systems of equations. Let's do a warm-up. Points A and B are 100 kilometers from each other. Common and Kaylee each start at points A and B and start riding their bikes at constant speeds towards each other. Therefore, the total distance they each travel relative to how long they travel remain a linear function. 1 hour later, Kaylee is 80 kilometers from A, and 2 hours later, and here, this is not 2 hours after this, it's just 2 hours later, so 1 hour after Kaylee is 80 kilometers from A. Common is 30 kilometers from A. How long did it take for the two to meet? Name your approach and discuss. Okay, so this is another itinerary problem. First, we can create a diagram. We know that they start at points A and B, and then they go towards each other. This is the part when Kaylee is 80 kilometers from A, and this is 1 hour's ride. 2 hours later, Common is 30 kilometers from A, so this is where he is. So this is Common's solution. All right, we're using the same names. Yeah, okay. So this is his solution to his problem. You can graph the relationship between the S and T of Common and Kaylee respectively and find the x-coordinate of the intersection point. So here is a Cartesian coordinate system, and we're just going to graph their speeds. And their intersection point is where they meet, right? It's where their distances from A are the same. Now this is Karen. Now here's her solution. For Kaylee, S is a linear function of t, so we can set S is equal to kt plus b, where S and t are variables and k and b are parameters. K and b are coefficients. When t is equal to 0, S is equal to 100. When t is equal to 1, S is equal to 80. After substituting the variables first into S is equal to kt plus b, we can find out the values of k and b. That is, the function expression between S and t for Kaylee can be found. The same way can be found for common. So she's asking, can you find the function for common? What she's saying here is we don't know that linear function. We don't know their speeds. So all we're doing right now is first assuming that the linear function is s is equal to kt plus b. Right now they're all unknowns. S and t are the variables, and k and b are the coefficients that we don't know yet. But what we do know is that after we put this input value t, which in this case is 0, into this linear function, the output value s that comes out of it is 100. We know that if the input value t is 1, we put it through, what comes out is the output s, and that's equal to 80. So after solving that, so then after we put this in here, we have two linear equations that we can write as a system of equations. This may sound really confusing right now, but I promise you this is what we're going to get better later, okay? So this is what we can get. Solved, s is equal to 300 over 7, t is 27. 1 hour later, Kaylee is 80 kilometers from A, so her speed would be 20 kilometers per hour. 2 hours later, Condon is 30 kilometers from A, so his speed is 15 kilometers per hour. Assuming that they meet at t hours after starting at the same time, then 15t plus 20t is equal to 100. Therefore, t is equal to 20 over 7. So these three kids, they all used three different ideas to solve this problem. Kami wanted to use graphs. Karen talked about using systems of equations, and Kaylee was our final one. She said to use linear functions. So what inspired you from their discussion? What did you learn? What did you observe? How can you apply this to your own problem-solving thinking? The graphic method can obtain results of the problem intuitively, but sometimes it is difficult to be very accurate. So in order to obtain more accurate results, we generally use algebraic methods that include equations and functions. This says functions, this is supposed to be functions. Example 1. A long-distance bus terminal stipulates that passengers can carry a certain amount of luggage for free, but if it exceeds the amount, they need to buy a luggage ticket. And the luggage for YUSD, US dollars, is a linear function of the luggage mass, x kilograms. It is known that Karen brought 60 kilograms of luggage and paid a luggage fee of 5 USD. Kaylee brought 90 kilograms of luggage and paid a luggage fee of 100 of 10 USD. So first, write down the linear function between y and x. And 2, how many kilograms of luggage can a passenger carry for free? Okay, here for the first question, we can set the unknown linear function as y is equal to kx plus b. This is sort of like setting variables, but this time we're setting another unknown value, and that's the linear function. From the information given in the problem, we know that 5 is equal to 60x plus b, and 10 is equal to 90k plus b. Solved, k is equal to 1/6, b is equal to -5. So therefore, after plugging this back in, we have the linear function y is equal to 1/6 x minus y, minus 5. Now here's number 2. All we're doing is, now that we have this linear function, we're trying to look what input value x do we have to put in so that the output value y is equal to 0. And you can really just substitute y is equal to 0 first and then solve for x. So x would be equal to 30. Therefore, each passenger can carry at most 30 this is not supposed to be kilometers, this is supposed to be kilograms, kg of luggage for free. Here's our conclusion. First, set the unknown linear function expression in the form of y is equal to kx plus b, and then substitute the coordinate pairs given in the problem to find the coefficients. This is called the undetermined coefficient method. A general step to solve using this method is to first set the unknown linear function as y is equal to kx plus b, substitute the known coordinate pairs into the linear function, solve, and then find the expression of the function. Example 2. Given that a linear function goes through the points 3, 5, x is equal to 3, y is equal to 5, and x is equal to negative 4, y is equal to negative 9, find the expression of this function. Well, first, set this unknown expression as y is equal to kx plus b. Substitute in each of the points 3, 5, and negative 4, 9. So you know that 3x plus b, so when x is equal to 3, y is equal to 5, right? So 3x plus b is equal to 5, and negative 4x plus b is equal to 9, negative 9. And now you have a system of equations. Solved, k is equal to 2, b is equal to negative 1. So the linear function would be y is equal to 2x minus 1. Now you do some practice. It is known that the graph of a linear function passes through the point negative 2, 4. The expression of this linear function is, pause the video and use the steps that we used to solve the other examples before to solve this problem. Well, the general steps are still the same, right? You first set that unknown expression as y is equal to kx or mx plus b. And then you substitute the given coordinate pair in. You'll get y is equal to negative 2x. If the graph of the linear function y is equal to kx plus 5 passes through the point negative 1, 2, then k is equal to what? Well, after substituting this in, you can just substitute x as negative 1 and y as 2. So k solved would be 3. If the graph of the linear function y is equal to 2x plus b passes through the points a7 and negative 2a, then the expression of this linear function is, again, what? Well, first you can set your unknown linear function, so that's y is equal to kx plus b, right? And then after you substitute your values in, your given values, you have a system of equations, solve it, and then put the values of k and b back in. You have y is equal to 2x plus 5. Example 3. Given that a linear function goes through 0, 2, and the area of the triangle enclosed by the function of the two axes is 2, find this linear function. Even though this is an example, I still want you to pause this video and see if you can figure this out by yourself. So of course you could use this using the graph method, and you could, count all the squares and stuff, but here we want to use the algebraic method to be more accurate. So set the unknown linear function as y is equal to kx plus b with k not equal to 0. And this linear function passes through 0, 2. Therefore, b is equal to 2. The x-intercept is negative 2 over k, 0. Then 1/2 times 2 times the absolute value of negative 2 over k is equal to 2. Solved, k is equal to 1 or negative 1. So the expression of the linear function is y is equal to x plus 2 or y is equal to negative x plus 2. Before we move on, I just want to talk about how in this problem there were two multiple answers. So k could have been 1 or negative 1, resulting in two correct answers. Now you won't get this problem right if you only wrote down one of them, okay? You have to write down both because now it's not a simple question like what is 2 plus 4 or what is 8 times 8. There's multiple answers now, so you really want to make sure you're thinking fully. You're thinking about all the different possibilities that could happen. Class summary. We learned all about determining linear functions using systems of equations. First, we set the unknown linear function as y is equal to kx plus b. Then we substitute the given coordinate pairs in the problem into this linear function right here about k and b. Solve the system of equations to get k and b's value, and then substitute those back into the linear function here, and then you have the answer, you have the expression. The skill we learned today is to express is to find the expression of the linear function is that the expression of the linear function can be determined by using a system of linear equations in two variables. This is part 2 of our binary linear equations and systems of equation and linear functions lesson. So if, again, you would like to revisit the last lesson to recover on some information you might have not watched yet or not remembered, then again, the link will be down in the description box. If you would like to check that out, I highly recommend you to do so. Thank you so much for watching through Inquisitive Kids, and see you next time.